about now is the ionic basis for a pacemaker cell. Now I talked about we've got two major types of cell here. We've got pacemaker cells, we've got contractile cells. So we're going to look at the pacemaker cells first. These are the cells that spontaneously depolarize. They have this autorhythmic ability. And so what this really means, I want to make sure that you understand what's happening here. We're seeing the manipulation of the membrane potential. Remember, an action potential, a potential of any sort is really just a manipulation of different channels opening and closing. We talked about the idea that if a lot of sodium rushes into the cell, that's a positive membrane potential change that's going to depolarize the cell. If a lot of potassium rushes out of the cell, that's going to be a negative membrane potential change that's going to repolarize the cell. So the similar principles that applied as we talked about an action potential on a neuron or on muscle or other excitable cells, they somewhat apply here, but here we're seeing this happen completely spontaneously. And so we start out with a spontaneous depolarization, which is really caused by a closing of potassium channels and an opening of two types of channels. We see the opening of a potassium-sodium channel. This is called a funny channel. And so I'm going to write in brackets here. Oops. I'm going to write in brackets here because it's not on this text, but this is another reference for this type of channel. This is called a funny channel. And a funny channel allows both sodium and potassium to move. But because we have closed potassium channels, so this is the first thing that we did. We closed the potassium channels and we open up these funny channels. And because we've got now a net positive movement, we've got a net movement of sodium into the cell, this ends up being a net depolarization. The second type of channel that allows for the spontaneous depolarization is the opening up of calcium channels. And calcium channels are kind of the same idea here, a lot of positive charge. This is actually 2+ positive charge. Calcium comes into the cell. That's also going to be a positive membrane potential change, which will also lead to further depolarization of this cell. Now, these two events, right, the closing of potassium channels and opening up of funny channels, along with the opening up of these initial calcium channels, are going to lead, and we can sometimes call these slow calcium channels. I'll put that here in brackets. Okay, these two events are what are going to bring the cell to threshold. When we get to threshold, because of these two initial events, we then open up fast calcium channels. And these fast calcium channels are what are going to actually give us that rapid spontaneous upward stroke, very similar to what we saw sodium do in a neuron. We see that rapid upstroke in the membrane potential, which is the action potential. So the action potential, the upstroke of the action potential is really caused by the opening up of these fast calcium channels. After that rapid upstroke in the membrane potential, we then see an opening up of those potassium channels. So remember, we started out with these channels closed, and we can now open them, and that is going to lead us to repolarization. And we know that this is because we open up potassium channel, potassium always wants to leave the cell. As that positive charge begins leaving the cell, we now see that membrane potential restored back down to rest. Again, very similar to what took place in a neuron. Okay, so that's kind of the basis for the electrical activity of the spontaneous depolarization of a pacemaker cell. Okay, let's look here at kind of a graphical representation of that. So we start out with our channels closed, our channels open. And the first event that happens is we open up funny channels and we close potassium channels. So this green upstroke, or this slight green depolarization from rest, is caused by the two initial events, the opening up of funny channels and the closing of potassium channels, as well as the opening up, so that's going to be the initial depolarization. Then we see the opening up of the slow calcium channels. So that's the part of the graph here shown in pink. And that is the opening up of those initial slow calcium channels. And that is going to increase the membrane's permeability for calcium, which will also allow for this rushing of calcium into the cell. And then we're going to get to threshold. And then from threshold, we now open up the fast calcium channels, which is this orange part of the curve. And that is going to be the rapid depolarization of the pacemaker cell, which is the action potential. And then at that point, at the peak of this graph, we then see the opening up of the potassium channels and the closing of those fast calcium channels. And then that is going to completely repolarize the cell back down to rest, okay? And so these are the events that are responsible for the action potential in a pacemaker cell. Okay. Let's look at a contractile cell. So a contractile cell we mentioned earlier does not have autorhythmic ability. It needs to receive the electrical impulse from the gap junctions that are connecting these cells to some of the other conduction cells and pacemaker cells. And so the ionic basis here is going to be different than the ionic basis that we just saw in a pacemaker cell, because these cells do not spontaneously depolarize. And so we've got 5 steps or 5 phases of the electrical activity here in this type of cell. The first phase is that we increase the permeability to sodium. So sodium rushes into the cell. This is what's responsible for the rapid upstroke of the action potential in a contractile cell. So that's kind of the first thing you want to really make a note of, is that the upstroke of the action potential in a pacemaker cell was caused by calcium. The upstroke in the action potential of the contractile cells are caused by a different ion altogether. It's caused by sodium. So we have that rapid upstroke in sodium's permeability, which allows sodium to rush into the cell. And then phase 1 is that we see a decrease in sodium's permeability, which begins to start repolarizing the cell. Now, the next 2 events are going to be what allow this kind of lingering of the membrane in this depolarized state. So instead of completely repolarizing the cell by closing those sodium channels, which is what would have otherwise happened, we now see the opening up of calcium channels and the closing of potassium channels, and that creates this plateau phase. And so because we open up calcium channels with this increased calcium permeability, we now see that the membrane does not rapidly repolarize. Instead, it kind of lingers in this depolarized state as this positive calcium starts entering the cell again. And then we decrease the permeability to potassium. This is helping to prevent or delay that repolarization. The purpose of phase 2, the purpose of the plateau phase, is to allow for more calcium to come into the cell. We talked about the fact that in smooth muscle cells, also in cardiac muscle cells, the source of the calcium that allows for muscle contraction is not only from the SR, but also from the extracellular fluid. And so allowing this phase 2, allowing this kind of delay, this kind of stalling of the membrane permeability so that more calcium can come in, is a way to bring that extracellular calcium in to help with the actual contractility that's going to happen in these contractile cells. So after we've kind of stalled here for a bit by phase 2, we can then progress to phase 3, which is where we kind of flip-flop these 2 channels. We close calcium channels, open potassium channels. This allows the membrane potential to continue repolarizing until it gets back down to rest. Okay. I want to point out here that the duration of cardiac muscle cells, smooth muscle cells as well, is much longer than skeletal muscle. For a cardiac contractile cell, its action potential is anywhere from 250 to 300 milliseconds when compared to the very brief 1 to 2 milliseconds of a skeletal muscle fiber. And this is actually why we call skeletal muscle contractions twitches, because they're just so brief when compared to smooth muscle contractions and to cardiac muscle contractions. Okay. So here is another graph that kind of simplifies or shows a representation of the events of a contractile cell. So here we start off at a slightly more negative rest. So I want to point that out here. The resting membrane potential of a contractile cell is more negative than it is for a neuron, more negative than it is for a pacemaker cell. So we start off at about -90, and we initially have the upstroke of the action potential as the first event that we see. This is phase 0. So we open up sodium channels, the membrane permeability for sodium drastically increases and sodium rushes into the cell. This gives us our positive upstroke, positive membrane potential change, which is the action potential. Then we begin to repolarize. So when we close those sodium channels initially, this very small downward inflection of the curve here, where we see this closing of the sodium channels, is an attempt to begin repolarizing the cell. And if we didn't do anything here, this would just completely repolarize back down to rest. But because we need to kind of stall this depolarizing event, because we need to kind of keep the cell depolarized for slightly longer to allow for that movement of calcium to come into the cell, we have this plateau phase, which is phase 2. And the plateau phase, shown here in pink, is where we now open up calcium channels. This is going to kind of linger the cell in that depolarizing phase as more calcium starts to come in. But it's also going to be important because that calcium is what we need for the actual contractile machinery of the sarcomeres in this cell. And likewise, we will close potassium channels to prevent the cell from repolarizing as we kind of stall the cell in this plateau phase. After we've allowed for enough time, so you can see that this is a horizontal curve, meaning that this is going to take quite a bit of time. This is what is going to allow this kind of stretching out of the duration of the action potential here. And then we see the flip-flopping of those channels where the potassium channels now open, calcium channels can close, and that is going to allow the complete repolarization of this cell as calcium is no longer moving, potassium is rushing out of the cell, and that we know is a repolarizing event. Okay, and then we get back down to phase 4 again, which is where we have an increased permeability for potassium. So potassium channels are moving here, and we know that that is going to keep the membrane potential closer to potassium's equilibrium potential. And sodium channels are closed, calcium channels are also closed. Right, so here's another illustration of the same series of events, right? We start with phase 0, then phase 1, which is where we try to repolarize, and then we have that kind of stalling or that plateau, that kind of lingering phase, which is phase 2, and then we can continue with repolarization, and then we get down to rest. So the important concept, the important take-home point here is that phase 2 is really just interrupting the repolarization phase. It's just kind of stalling or lingering in this depolarized state for the 2 reasons that I mentioned: to actually keep the cell depolarized, but also to allow for the movement of calcium that's really important for the contractility of a contractile cell. And so when you look at the other properties of cardiac muscle cells here, we also see the excitation, contraction, coupling mechanism the exact same way that we saw it for skeletal muscle. So we've got T tubules, we've got the sarcoplasmic reticulum that has calcium, we've got the troponin and tropomyosin regulation. We've also got those DHP and the ryanodine receptors, if you remember those 2 receptors that were coupled to each other, DHP being the voltage sensor, ryanodine receptors being really the voltage sensor, but also the calcium channel that allows that calcium to move from the SR out into the sarcoplasm. So those are shared properties that are similar to skeletal muscle. But then there are some other properties that are shared with smooth muscle as well. The fact that we have gap junctions here, the fact that the source of calcium is not only the SR, but also that extracellular fluid where we have calcium coming in as well, okay? So bear in mind some of the shared properties between other types of muscle and some of the different properties as well. So let's look here at the steps or the events for the excitation contraction coupling in a contractile cell. And it's very similar to what we saw with skeletal muscle in some ways and with smooth muscle in some ways as well. So the first thing we see is that the action potential arrives to this cell via a gap junction. Okay, it's coming from a gap junction, either from another contractile cell that's neighboring or from another autorhythmic cell, a pacemaker cell, a conduction fiber, but the action potential gets here through a gap junction. It arrives on this cell and it depolarizes this cell. It allows for the electrical activity to travel throughout the cell, which is going to allow for the first event, which is for sodium to rush into the cell and then to start trying to rush out. And then the second phase, the plateau phase of the action potential here correlates with the third step that we see here in this schematic. This is where calcium can now start to really enter the cell from the extracellular environment, but also from the SR where it's being stored as well. From there, everything is pretty much the same as what we've seen with skeletal muscle. Calcium enters the sarcoplasm here, binds to troponin, it drags those tropomyosin, fibers away from those binding sites. Myosin can interact with actin, the whole cross-bridge cycling can happen. And then in order to get rid of that calcium from this cell, we have two routes here. Very similar to what we saw with smooth muscle, because we have two sources of that calcium, we also have two routes of that calcium leaving the cell. One is that it gets pumped back into the SR by a calcium ATPase pump. The second is that we can exchange it across the cell membrane for sodium. So remember, sodium wants to get into the cell at the top here. Sodium wants to get into the cell. I don't know why my pointer isn't working. Okay, so sodium wants to get into the cell according to its ECDF, and then calcium also wants to get into the cell according to its ECDF. And so in order to get calcium out, that's going to need active movement. And so we're going to take the energy from sodium moving passively and use that to move sodium in the opposite direction, that antiport that we talked about, or that secondary active transport mechanism. We can also have active pumps on the membrane. So it's kind of a third mechanism here. We can have active pumps that are coupled to ATP, which is primary active transport, that are just simply pumping this calcium out of the cell as well. So kind of three main mechanisms for clearing the cell of calcium and ceasing the muscle contraction here in cardiac contractile cells. All right, so the relaxation of a cardiac muscle cell relies on the removing of that calcium from the cytosol. We talked about this idea. If we don't remove that calcium, it's going to remain bound to troponin. It's going to keep actin and myosin interacting. It's going to keep cross-bridge cycling going. And in order to cease that, in order for this muscle to relax, we must remove it from the cytosol. And we talk about these three mechanisms here, which are pumping it back into the SR, pumping it back across the plasma membrane back into the extracellular fluid, or exchanging it by a secondary active transport across the plasma membrane in exchange for sodium. All righty. All right, any questions thereof? We've got 2 minutes left. I'll probably pick up with the electrical activity, so the ECG, and how we use the ECG to measure electrical activity. We'll probably reserve this for Monday. And I'll just kind of linger here and see what questions you have for a minute or so. And so we'll pick up with this on Monday, and then we'll look at a few practice questions, and then we'll move into the cardiac cycle, which is packet 3. So someone's asking about the graphs. Yes, they're all posted. So I posted a combined PDF that has all the cardiovascular drawings, and it's got both of these graphs on there, as well as the kind of the flow of the conduction of the electrical activity, that first drawing.